أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله. So welcome back to the lectures. Today we start actually basically this is lecture 9 from the last week. So this is kind of a replacement lecture. So in this lecture we will start a new chapter which is called Magnetostatics. So means we will learn about the magnetic field, magnetic flux, and so on, and other things related to magnetism. So this is a part 1. Possibly we will have like three parts for this specific chapter, or maybe less. So without any further delay, we go to our topic. So we will discuss first about the magnetostatic fields. So far from all the lectures, we already have covered, that due to the constitution of the Coulomb's law, we find out our electrostatic fields. Means any kind of stationary charge actually produce static electric field. So with the same actually, at the same time, if we have there is another law actually, which is actually Biot-Savart law, which actually constitutes for the magnetic field. It actually says that that when any charge moves at a constant rate, means it doesn't change any directions, so it actually generates a static magnetic field. Actually, it means that any charge which is static is not moving. It means it have only electric field components. But that charge, if it's started to move in a certain direction without changing any directions, let's say from negative to positive or positive to negative, it actually produces a constant static magnetic field. On the other hand, actually, if we continue with this study, that if a charge or a group of charges which moves along the direction, let's say from positive to negative and negative to positive and so on and so forth, this will produce actually called alternating current, and in terms it will produce which will have a mixture of both electric and magnetic components moving along one certain direction, we'll call the electromagnetic fields. So now we distinguish three things. So according to Coulomb's law, stationary charge produces static electric field. Now when the static electric field starts moving with a certain direction without changing any direction, it produces a magnetic field, and which is constituted by which is shown by the law of the Biot-Savart. Later on we will learn about it, actually how it works. And the third one, which is actually the electromagnetic field, means when a charge is actually moved from positive to negative and negative to positive and so on and so forth, means it changes its direction, it actually produces the electromagnetic field. But our discussion is not this one today. Our discussion is related to Biot-Savart law and anything related to static magnetic field, which is actually we call magnetostatic field. Here we can check a very quick abstract difference between these three scenarios, which is electrostatic, magnetostatic, and electromagnetics. So a stationary charge produces static electric field, which is actually I already told you, and then a static current means a current which doesn't change any direction, which produces the static magnetic field. And the time varying current means that due to the time, when the time passes along, it changes its direction, means from positive to negative and negative to positive. So it's called dynamic electric and magnetic field, which is we call it electromagnetic field, which have to be time varying electric field. So it means the electric field will produce a magnetic field together, and together the mixture of electric and magnetic field produces electromagnetic field. There is one more comparison here actually. This is what we call constitutive equations. There are three actually constitutive equations, which is based on the electric field and electric flux density and magnetic field and magnetic flux density. So for electric field, we know already that electric flux density is equal to epsilon multiplied by the electric field, which is actually called the permittivity. So electric permittivity, we know it already. So, but total permittivity is actually relative permittivity multiplied by the permittivity of the free space. So multiplication of these two actually constitutes the total permittivity. So from here we know that D is equal to epsilon E is equal to epsilon R multiplied by epsilon naught E. So this is what we know already, but for magnetic field, more or less similar, but we introduce one more thing. So, rather than electric permittivity, we put magnetic permeability, which is mu. And B is the magnetic flux density, and H is the magnetic field, or you can call it vector magnetic field. So this is the so B is equal to mu, which is called mu. Mu is actually the permeability of a magnetic field. So for magnetic field we use permeability. For electric field we call it permittivity. So here the equation is B is equal to mu H, and also similarly like the permittivity, mu is equal to mu R multiplied by mu naught. So if this 2 is given, you can calculate this one. Later on we will actually derive how actually this equation comes. So these will be given actually in the exam if you ask any kind of questions of this one. The total amount of all the constant will be given. So don't worry about it. In the exam, the constants will be given. So far, we know clearly about these two constitutive equations. Now we go for the third constitutive equation, which is common for both, which is J means the current density. So current density is for electric field and magnetic field is the same, but there is one more parameter it introduces, which is called the sigma. What we learned already, that sigma means the conductivity of any medium. So it have to be in any medium. So J is equal to sigma E, and then now we have three medium characteristics, which is called the constitutive parameters, which is mu, epsilon, and sigma. Permeability, magnetic permeability, electric permittivity, and the conductivity of the medium. So these are the basic comparison between the electric and magnetic fields. So where you can take a look at these things, that you can get a clear idea about how these two different equations actually constitute two different parameters, and represents actually basically not constitutes, represents two different parameters. So basic laws, we know this one. So you need to study a little bit about it. So this will be given in the exam. If you need to if any question asked from here, you can answer from here. So we directly go to the Biot-Savart law. So here the Biot-Savart law, basically what I told you already, that it says that a magnetostatic field is produced by a steady current. So where let's say this is this is the wire, where the the current is moving through, and the current, it doesn't change its path. So at P it will feel some magnetic field, so which is actually, we call it that dH if it's a small for dl, for a small distance of dl, we have a very small amount of magnetic field of dH, which is proportional to the current multiplied by the dl and the inverse square of the distance between them, and there is a constant here 1/4 pi. So this equation actually it comes from the from the previous few lectures ago actually. So but I don't want you to go so deep inside this one. You just need to learn about these things, that the I actually have a cross relationship, not dot relationship, because magnetic field always will follow the cross, not the dot. Unlike the electric field is always follows the cross dot. Dot. It will always the magnetic field will always follow the cross. So I cross R is the main basic situation here. But we know that if we make a cross operation between two vectors, that we have IR sine alpha or theta. It can be theta, it can be alpha also, but it's a angle between the tangent point and towards the radial direction of the P. So this is the angle. It can be also called theta, which we will call it in theta in the next derivation. So from here we get IR sine theta, which is take away one of R, and then we get this one. So we need to remember this one, that the magnetic field is equal to I sine alpha. So the I sine alpha and 4 pi R square d L bar, which is towards this direction. So, but the thing is, this is magnetic field. So how we can calculate now the magnetic flux? So which is actually follows this. So Biot-Savart law, what actually it says that if there is a wire and a current through any wire passing through, and there is a point P from where we need to calculate or we need to measure the electric flux of the of electric flux due to this wire at P point, then there are few laws we need to follow. How? The electric flux is proportional to the length, the smaller length means the differential length, and the total current at this direction. So I dl. So the dB is proportional to I dl. And another constitution is that the magnetic flux will be proportional to the inverse square of the distance from the middle point of dl and P, which is 1/r square. And the last proportional will be that the electric flux is proportional to the angle between the direct distance and between the current carrying wire, so which is theta. So from here we said alpha, here we said theta, but it's mostly the same thing. So we have these three identities now, which can actually by the law of the proportionality we can actually add them. If you add them, make them one proportional, then it becomes this multiplies with this and divided by this one. So I dl sine theta r square. Now to make this one equal, we need to introduce one constant, which is mu naught 4 pi. So this by this one, this dB means the electric flux is equal to mu naught 4 pi I dl sine theta r square. But as we know that from here, it can say that this is totally the whole thing actually. The whole thing is actually dH. So this dH, we put it here. So and then only the mu not, or we can call it mu actually. It says here. So the dB is equal to mu dH, and if we integrate them, we got B is equal to mu naught H. So this is how we got B is equal to mu naught, which is actually from here. So that's how easily we can actually calculate this one. Now this is the current carrying, right? Now if we go to another situation for a line current, not like a wire or something. If it's a line current, then how? So let's try to put some values and try to calculate this one. Now for the line current, we have a very small, let's say dl becomes dy here, and theta is theta, and r we keep it here. Now this value becomes a. Okay, so this one we got it from here for sure, we know it. So we got it from here, and then sine theta, this is just trigonometry. So a divided by root over a square y, from here actually we got it. So a divided by root over a square y square, which is this one. So r equal to become root over a square y square. So we actually replace this one values in equation 1. So we find it here, and then so on. This is dy, dl we replace by dy, and then it becomes an actually basically the integral. So if we integrate this side, we get total b. So we have b, and then if you integrate here from y infinite to y minus infinite to y plus infinite, then actually we get something like this. So the b is equal to actually mu naught I twice pi. So if you know about the medium mu naught, and you know the distance, the direct distance from the wire, not from here, the direct distance, this one, and then if you know I, then you can easily calculate the the magnetic flux of any current carrying wire. And similarly, you can find H means the magnetic field strength by I divided by twice pi A. So now we move on to an example. A very simple example says that determine the magnetic field at the center of the current loop in the shape of an equilateral triangle which have a side length of 4 meter carrying a steady current of 5 ampere. So this is a loop which is actually carrying the 5 ampere current. So it's constantly revolving through, and it says that the length of L, this is L, is 4 meter. So if this is 4 meter, this is 4, this becomes also 4 meter. So now we need to find out the magnetic field due to this loop. So now we go to the solution. See that if it's we need to find the middle point first. So if this is a equilateral triangle, so the whole thing is 60, right? So if you draw a line at the middle of the next next side, so it actually bisects the angle, which becomes 30. So by this law we know that tan 30 is equal to d divided by, so means this divided by this. So we know L is equal to actually 4. So from here we can actually find the distance d. So here we find 1.155. So 8 segment, we can find it from twice pi rho root over rho square z square minus a, which is actually rho is equal to d, basically, because this is the distance from z naught Okay, so and z naught is equal to L. This is L by 2, right? So this point is L by 2, so it is 2 meter. So from here we have 2, and then this we know rho, we know z, we know I. So from this value actually we put here, then we get actually H segment. But H segment basically, let's say there are 3 segments, right? This is 1, this is 2, and this is 3. So they are actually identical. So when we multiply the H segment with 3, we get H total. So that's how actually we get our final value of minus 1.79 AZ ampere per meter. So that is the value of our magnetic field strength. Now from here actually, if you want, you can easily find the magnetic flux by using this equation. This equation. So B equal to mu H. You can use mu naught if mu naught is given. So that's how as easy as like that. So now here, if it's not a line current anymore, it's a loop current. If it's a loop current, circular loop current, then that is a little bit different, but not so much. These things I don't want to go so deep because you know it already, but you go through this one, how this comes, and then there is a derivation here, and then after the derivation we get H is equal to I by twice A. It means if it's a loop current, or a circular loop current, you don't need to multiply with pi also. See the difference between here? That's here. I, for the line current, I divided twice by A, right? But for the loop current, here check, I divided by twice A only. So if you know the radius of the loop, then your current electric field is the magnetic field state is already known. If you know the magnetic field, then you know the magnetic flux also. So that's the end of our lecture 9, and this is another attendance assignment for you for lecture 9. So I will later on put up a portal for this one. So you need to solve this one. Basically, this is same as the equation, a little twisted, same as the as what we have done here. Most like this. I twisted it a little bit. Try to understand, and then you can answer. So that's all. Lecture 9 is finished. Soon I will upload lecture 10. Assalamu alaikum.